Okay, good afternoon, everyone. Welcome to lecture 14. That's the final lecture of Teorija izračunljivosti, computability theory. So today we're going to complete the academic material of the course by looking at one of the strangest theorems, I think, in computability theory. That's called the recursion. Maybe I'll put a bit more space there, a bit less space. That's called the recursion theorem. And an application of it, which is to prove something called Myhill's theorem. The same Myhill as in the, oh, actually, I don't think we did maybe we haven't seen any other results by Myhill. There's a famous result called the Myhill-Shepardson theorem, but actually we didn't do that. Anyway, we are going to do Myhill's theorem and the recursion theorem. So Myhill's theorem is a theorem that one can tell a story for why it's an interesting theorem. Whereas the recursion theorem is particularly interesting because of its curious form. I mean, the statement of the theorem is just something rather strange. It's a kind of, it's a peculiar kind of fixed point theorem. And in some ways its interest is in its peculiarity. Its proof is also a little bit peculiar, but it has quite a lot of applications. In fact, if one does computability theory at a more advanced level, the recursion theorem is one of the most useful tools that exists. Okay, so we'll start our way by working our way towards Myhill's theorem, but basically what it's to do with is to do with the concept of reducibility. So we've already met the concepts of reducibility. We had partial reducibility and total reducibility. So here we're just going to look at total reducibility. So for sets, or subsets of the natural numbers, for sets of natural numbers, we have A is reducible to B. So just remind you of the definition, and that's defined to be there exists a total computable function f that reduces the membership of A to the membership of B. So such that for all natural numbers, we can find out if n is in A by testing to see if f of n is in B. So n belongs to A if and only if, so n belongs to A if and only if f of n belongs to B. This is total reducibility. It's also called many-one reducibility. And because it's called many-one reducibility, we're going to introduce a notation for it. The set A is less than equal sub M, meaning under many-one reducibility, to the set B. And the intuition is somehow, from a computational perspective, A is a less complicated set than B, or B is a more complicated set than A. So we can reduce less complicated sets to more complicated sets, but we can't reduce more complicated sets to less complicated sets. And I'll say a little bit more about that in a moment. So intuition, B is computationally at least as complicated. It's an intuition, so we don't need to know precisely what complicated means as A. Or A is no more complicated than B, if you like. And this is justified by previous results, which we can summarize using the new notation. So so a proposition summarizing previous results. So the idea, if A is no more complicated than B, if we have a positive computational property of B, then we can use the reduction from A to B to derive that A has the same positive computational property. So what are positive computational properties? They're properties like B is a computable set, that is a decidable set. So if B is a nice, simple, decidable set, then A will also be a nice, simple, decidable set. So this was the reduction lemma when we first introduced the reduction relation. So if maybe I'm going to put this on the next page because there's not really enough space. So this is justifying, this proposition is giving examples of the way in which this relation says that A is no more complicated than B. So let's start again. Proposition summarizing previous results. So suppose A is reducible to B, then, so firstly, if B is computable, then A is 2. I've already talked you through that. And anyway, it's an old result from the reduction lemma. If B is computable, then so is A. Very similarly, if B is need not be computable, but suppose B is computably enumerable, that is only semi-decidable, then again, that's a positive computational property, being semi-decidable. And again, the reduction from A to B allows us to transfer the semi-decidability to A. That was again part of the reduction lemma. So if B is computably enumerable, then so is A. And in the other direction, so these are examples of A being no more complicated than B. In the other direction, B is at least as complicated as A. So if A has some negative computational property, some absence of goodness computationally, then that propagates up to B. So if, for example, if obviously the contrapositive of this, if A is not computably enumerable, then neither is B. But last week we saw a stronger property than being non-computably enumerable, which gets transferred by reduction. and that was being productive. So that's a negative property. That's saying it not computably enumerable in a strong way. And last week we saw that if A is productive, then so is B. So remember, productive meant that if we have the index for a computably enumerable subset of A from any, we've got a computable function that given the index for, given any index for a computably enumerable subset of A, returns an element of A that is not contained in the subset. So it's a strong way of witnessing that A is not itself a computably enumerable set. Okay, so these are three results that all indicate three different ways in which B is at least as complicated from a computational point of view as A, or A is no more complicated than B. And the reason for introducing this notation, well, we want to talk about reducibility, we want a shorthand for it. We're using an order relation, and that's rather natural because so sorry, I just want to check that I'm going to do things in similar order to in my notes. Okay, so that's some properties of the this relation. So firstly, it is a preorder. That means it is reflexive. So any set is less than or equal to itself and transitive. If A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. So it is what's called, these 2 points say it is what's called a preorder, or people used to call it, people sometimes say quasi-order or quasi-order if you're American. I'm glad I'm not American at the current time. So another simple property you can show is that if one set reduces to another, then just directly by the definition of reducibility, by this reducible means you can reduce testing membership of A to testing membership of B. It immediately follows from that it's equivalent for A to be reducible to B as for the complement of A, that's the set of all natural numbers not in A. I won't bother to write that down. I've introduced the notation several times before. The complement of A, the set of all natural numbers outside of A, is reducible to the set of all natural numbers outside of B, because any total computable function that reduces A to B by the same definition, by the definition of reducibility, the same function reduces the complement of A to the complement of B. And a slightly more interesting one, which I'll leave it to the exercise class to verify, which is that if we have a set that's neither empty nor the whole set, so it's not empty and it's not the whole set of natural numbers, then so for any non-empty and non-total set B of natural numbers, every computable set is reducible to B. So, and A is computable, then A is reducible to, whoops, that should be a sub M. So from a computational perspective, so we're understanding this relation to mean A is no more complex than B, or B is no less complex than A, and no set can be less complex than a computable set. Computable sets, they're decidable, and that is basically, that means there is, from a computability perspective, until we start talking about things like computational complexity, which is a different topic, from a computability perspective, no set can be simpler than a decidable set, that is, than a computable set. As an exercise, you might want to think about what the proper statements are for the empty set and what happens for the empty set and the natural numbers. So why we needed to exclude those two from consideration. Okay, so those are some basic properties of this reducibility relation. So the moral here or one of the morals is the relation is not very interesting, so it's not very discriminating. Discriminating means distinguishing between different categories of things. Is not very discriminating when it comes to computable sets. If you've got a computable set, then everything, excuse me, if you've got a computable set, then it is reducible to pretty much everything. And in particular, any two computable sets that are, if they're not empty and they're not the full set of natural numbers, are reducible to each other. So that raises the question, what about computably enumerable sets? Is there an interesting relationship of reducibility in general between I mean, we know there are many ways now, especially since last week, that computably enumerable sets might fail to be computable. They might be simple, or they might be, it's one strong way that they fail to be computable, or they might be creative. That's another strong way that they fail to be computable. So does the reducibility relation give us an interesting relation between computably enumerable sets? So we can say, yes, some computably enumerable sets are more complicated computationally than other computably enumerable sets. And in fact, we're going to introduce a notion that says, so what about, is there a most complicated kind of computably enumerable set? The definition is going to, well, we're going to make a definition that says a computably enumerable set has this property if it is basically of the most complicated kind of computably enumerable set. So a set, oops, let's put a bit of a space in there. So a set B is said to be M complete. So complete according to many one reducibility. If it is computably enumerable. So as I say, we're looking at different degrees of difficulty, as you like, of different degrees of complexity, as you like, of computably enumerable sets. And the most complicated kind, well, we would have a notion of a most complicated kind of computably enumerable set would be a set B that is itself computably enumerable, and such that for any other computably enumerable set, let's say for every, just to make it clear that this is really a universal quantification. So every other computably enumerable set is reducible to B. So every computably enumerable set is no more complicated than the computably enumerable set B. So of course, one can easily make the definition, but it might potentially not be very interesting because we don't know yet that any set is M complete. So let's immediately show that that M complete sets do exist, and our halting set K turns out to be an M complete set. So we have this notion of reducibility that allows us to say one set is no more complicated than another set. And in fact, no computably enumerable set is more complicated than the set K in terms of this reducibility relation. So K, the halting set, is in a precise sense the most complicated computably enumerable set. So let's prove this. So we already have from a previous lecture that, I don't even remember which one. The lecture on computably enumerable sets. We have that the halting set is itself computably enumerable. So all we need to show is that any other computably enumerable set is totally reducible to K. So, oops. So suppose A is a CE set. We must show that A is reducible to K. So we need to define a total computable function that will reduce membership of A to membership of K. And to define that, we're going to first define a binary function and then use the Smn theorem. This is a kind of standard technique that you've seen plenty of examples of in exercise classes now. So I'm not going to give too much chat about what's going on, and I'll just do it. But it's always useful to see these examples. So we're going to define a computable partial function. In two arguments. So, and the point of this is that whenever we fix X, we're going to get a total partial function in Y. So this partial function is only going to depend on X. And it's going to be defined if and only if X belongs to the set A. So if X belongs to A, we want this to be defined. And so I'm going to give back a number, and I'm going to give back 17 because that's the number I give back when all that matters is that we return a number. It doesn't matter which one. So here I'm signaling that all that matters is that we terminate by this definition. And if X doesn't belong to A, then we go into a loop. And this is certainly a computable partial function because we semi-decide, given the arguments X and Y, we ignore the argument Y, we semi-decide the membership of A. That will either go into a loop, in which case that's fine. We didn't want to return an answer. F didn't want to return an answer in that case anyway. Or the semi-decision process says, yes, X does belong to A, in which case we say, thank you for that answer. Okay, we will return the number 17. So now this is the two-argument function. The Smn theorem allows us to turn this into allows us to get a single argument function in X that for any X will give us an index for the function fx of Y for that value of X. So the Smn theorem a total function S of X such that f of X of Y can be computed by, so S of X returns the index for the partial computable function, which is f of X of Y for that value of X. So this returns so this should be, so this function applied to Y will give us back f of X of Y. So now, by the definition of F, by def of F, by the definition of F, we have that if X belongs to A, well, X belongs to A if and only if we apply phi of S of X to any argument at all, and X belongs to A, we get back 17. So if and only if, in particular, if we apply phi of S of X, if X belongs to A and we apply phi of S of X to any argument at all, we will get back 17. So this will be defined. So in particular, if we apply it to the argument S of X to its own index, then we'll also get back 17. Moreover, this will only give us back 17 in the case that this is f of X of S of X by this. And so this will only give us back 17 in the case that X belongs to A. So this is an if and only if, and this is saying, well, S of X is a number such that that number belongs to the domain of the computable partial function that it indexes. So that means this is just the definition of S of X belongs to K. So S of X belongs to K. So recall, maybe I should just write this in. Recall K is the set of E such that if we consider the E index partial function and apply it to the argument E, the answer is defined. This is the same as saying E belongs to W of E. So this says that S is a reduction from A to K, and that's what we wanted. So S is a reduction from A to K, and that was the thing we needed to do. So we are done. Okay, so there are M-complete sets. That is, there are sets that are as complicated as possible among computably enumerable sets. Perhaps every computably enumerable set is an M-complete set, apart from the computable ones, which are clearly different. But as it turns out, that's not the case. So the main result of the lecture, well, the recursion theorem is in some sense an equally strong result of the lecture. So one of the two main results of the lecture. So the first main result of lecture characterizes exactly what the M-complete sets are. These sets that are as complicated as possible as a computably enumerable set can possibly be. And this is Myhill's theorem. And this says a set of natural numbers is M-complete if and only if it is creative. So remember from last week, a set was creative if it was computably enumerable. So the M-complete sets, of course, have to be computably enumerable. That's part of the definition. Computably enumerable, and its complement set was productive. That was not computably enumerable in the strong way that I've already mentioned earlier in the lecture. So creative sets, that is computably enumerable sets with productive complements, are as complicated as possible among computably enumerable sets. And I'll end this part of the lecture with a proof of one implication of this. And this implication is actually really straightforward. So proof of the left to right implication. So that's that every M-complete set is creative. So suppose in my notes I've got B, so let's work with the set B. Maybe it doesn't matter. Suppose suppose it's M-complete. We need to show it's creative. It's creative. So creative means it's computably enumerable. So that's the first part. So it is computably enumerable because it is M-complete. That's part of being M-complete. So we need to show that, so it remains to show that the complement of B is productive. So we have that K is totally reducible to B because K is CE and B is M-complete. That's the definition of M-completeness. That's the hardness property, if you like, of M-completeness. Every computably enumerable set is reducible to it. So the complement of K is reducible to the complement of B. Remember, that was one of the facts about reducibility I mentioned earlier, that one set is reducible to another if and only if the complement sets are reducible. So last week we had, so by last week's lecture, we had that K is productive, the complement of K, sorry, is productive. And by another property last week that I already wrote above on the first sheet above, so we had that productivity was one of these negative properties, or well, it was the negative property that I showed transfers from left to right in reducibility relation. Hence by reducibility, by that fact that if the left-hand side of a set in a reducibility relation is productive, then so is the right-hand side. Hence, so is B, the complement of B by reducibility. And that's what we needed to show, that the complement of B is productive. And so we are done. Very good. So that's a good pausing point. We have Myhill's theorem that characterizes the creative sets, sorry, the M complete sets as being exactly the creative ones. We've shown the left to right implication. We will later use the recursion theorem and use that to prove the right to left implication of this characterization. Okay, so I shall pause the recording. Okay, so to start part 2 of the lecture, in part 1 we had the reducibility relation, and then the notion of a complete set, an M complete set under the reducibility relation, namely a computably enumerable set that's as complicated as it's possible for the computably enumerable set to be. We showed that the set K was M complete, and we stated Myhill's theorem that the M complete sets are exactly the creative sets. We have shown one half of that theorem, one implication of that theorem, namely that every M complete set is creative. And the remaining part is to show that every creative set is M complete. As I've already told you, that's going to require a new tool, which is the recursion theorem. And in this part of the lecture, we shall see what the recursion theorem is. But actually, before doing that, I just want to abstract away from some of these discussion on reducibility. And so we talk about a notion that's derived from the definition of reducibility. And the idea here is, so reducibility is somehow classifying the degree of computational complexity, not computational complexity in the sense of time complexity or space complexity, but just somehow computational complicatedness, if you like, complexity in that sense of a set. And we're comparing sets according to one set being no more complex than another set. So with this, it somehow makes sense to talk about the level of complexity of a set as somehow the degree of complexity of a set, to have some notion by which we classify sets of the same complexity as having the same degree. So we're just going to define a notion of degree that allows us to do this. so the idea here, so I'm explicitly calling them many one degrees because there are other notions of degree of complexity, such as a famous one is called Turing degrees. The idea here is that we're going to say that two sets that have the same level of complexity have the same degree, are given the same degree of difficulty, if you like, the same many one degree. So the degree is somehow a notion, a measure of the level of difficulty. It's almost like attaching a number to the level of difficulty, but it's not a number. So it's basically just, we call any two sets that, we say that any two sets that have the same level of complexity, that are reducible, interreducible, each one is reducible to the other, we say those two sets have the same degree. So, I mean, mathematically, it's rather straightforward. We simply use the reducibility relation to define an equivalence relation. So the equivalence relation between subsets of natural numbers, between sets of natural numbers, sorry, that should be a between. So between sets of natural numbers is simply defined by, so A has the same degree of difficulty, the set A has the same degree of difficulty as the set B. Well, it just simply means that A is no more difficult than B, and B is no more difficult than A. So they are interreducible to each other. And a degree, definition, a many one degree, but they're the only degrees I'm going to talk about, so I'm going to not talk about, I'm just going to call them degrees. Although usually if one talks about degrees in computability theory without an adjective, one means Turing degrees. But because we're only talking, oh, in fact, actually, let's do what's in the notes. Let's do the right thing. A many one degree, or M degree, that's a nice way of shortening it, is simply an equivalence class. Oh, my computer's going very slowly for some reason. Of the equivalence relation so the point is, rather than talking concretely about the individual sets of numbers, we can talk in general, we can talk more abstractly about the degrees they have. So whereas two different sets of natural numbers can be interreducible to each other, both those sets are characterized as having the same level of difficulty because they belong to the same degree. So the set of M degrees is the power set of the natural numbers, the set of all subsets of the natural numbers, quotiented by the equivalence relation. That's just saying, it's just another way of saying it's the set of it is the set of equivalence classes of that equivalence relation, and it has a partial order on it. One degree little a is less than or equal to another degree little b. So I'm following standard practice, which is to use boldface lowercase letters to represent degrees. So the underlining means boldface here. Let's again put a little m. And this is simply if and only if for if a is reducible to b for some a in little a and b in little b. And actually it doesn't matter. You can existentially quantify or existentially quantify this the sets a and b. So little a is a set of, is an equivalence class. So it's a set of subsets of the natural numbers. Whether you universally or existentially quantify these a and b, you get the same relation here. It's just because we started off with a pre-order on sets of natural numbers, we've gathered them up into equivalence classes, and the pre-order then turns into a partial order. So it also satisfies the anti-symmetry property of a partial order. And we can define that a degree is strictly now. So this is no more complicated than, this is somehow strictly less complex than the degree b. So the natural definition now is just as one expects for a partial order, if and only if a is less than or equal to b and a is not equal to b. So this is just another way of saying this is any set capital A in the degree little a is reducible to any set capital B in the set little b, but the reducibility in the other direction does not hold. So degrees give an abstract language for talking about these levels of difficulty, and the exercise class will look at this in more detail. So in particular, at theorem 14.8 in the LaTeX notes, which I won't state here because you're going to cover it in the exercise class. The LaTeX notes are already online. You don't need to look at it now until the exercise class, but basically this is a theorem that that restates some of the facts we've already seen about reducibility in the language of degrees to get you familiar with the notion of degrees. I just do want to correct the grammar here. This better be a comma and rather than a new sentence, because otherwise that sentence does not, the second sentence, because after the comma here, there's no verb. So that can't be a sentence in itself. Okay, so that's the notion of many one degree. There's somehow a degree of difficulty of a set according to the reducibility relation. Okay, so having done this, we can now change topic, and we're going to come to the curious recursion theorem. And this is yet another contribution of Kleene, who we've met many times in this course. Apparently Kleene's name was correctly pronounced kleine, but nobody pronounces it like that. I mean, amongst people I've heard talking about cleaning, I never hear anybody say kleine, so it just sounds very strange, but that was the way it was supposed to be pronounced. Not that it really matters. So we're going to now look at Kleine's recursion theorem. Actually, Kleine proved two theorems he called the recursion theorem. It was the first recursion theorem and the second recursion theorem. And the first recursion theorem he proved first, unsurprisingly, but it turns out to be a consequence, an immediate consequence of the second one. And the second one is far more interesting. So we shall just go straight to the second one, and we won't actually even bother to look at the first one. And this theorem, I'm just going to state it. And it's very short. So I'll just state it and then we'll see what it means. So suppose you've got any computable total function. So what it's going to say is that any computable total function has a sort of fixed point. So remember, a fixed point is a value that if you apply a function to it, the value stays fixed. It doesn't change when you apply the function. Now, of course, it's just simply not true that every computable total function has a fixed point. Consider, for example, the function x maps to x plus 1, the successor function on the natural numbers. Clearly, there is no natural number that when we apply the successor function to it, that natural number remains fixed. The successor is always a different number. However, every computable total function has a fixed point in the following sense. There is some number e such that if we apply f to that number e, then the result we get back is an index for the same partial function as the partial function indexed by e. Actually, I'm going to stick to the notation in my notes, which I just see uses n rather than little n rather than e. So the point is, for any, well, let's again make it clear that this is universal, just to be crystal clear. So for every computable total function f, there exists a sort of fixed point, so which is a natural number such that well, it can't be an actual fixed point, but the computable partial function indexed by f of n is the same as the computable partial function indexed by n. So there is some, applying this to the successor function, so applying this to the successor function, there is some natural number n such that the partial function indexed by n, phi of n, the partial computable function indexed by n, is the same as the partial function indexed by n plus 1. Very curious. And what on earth does that mean? Well, it's the sort of theorem that one can puzzle over for ages and really remain rather mystified by. But there are lots of peculiar applications of it. One of the applications is going to be the proof of Myhill's theorem, which is going to be the last thing we do in the lecture. many much simpler applications will be covered in the exercise class. I will do one other application in the lecture in a moment, but not immediately. First, I want to prove the theorem. So the proof is actually rather short, but it is rather mystifying. So it's the sort of thing you can follow what all the symbols are doing, but you don't really know where they're coming from. So I shall present it to you in symbols, and we can follow what it's doing in symbols. So using the universal partial function, remember that's our psi function, the partial function below, the part function below, which maps. So this is now where things get mystifying, because we have some quite clever definition of a partial computable function in two arguments. We map the two arguments x, y to the result of applying the computable partial function indexed by f of phi of x. So the x index computable partial function applied to x. We apply that to y. And this is a computable partial function because the universal partial function allows us to define this as a partial function in x. We're using phi of x, but we can get that computably, the partial function phi of x computably in input x using the universal partial function. So this function is computable. And now we're going to apply the trick we normally use with these binary functions, that we're going to apply the Smn theorem to get us an index for the function in y computably in x. So for any x, s of x will give us an index for this partial function on that value of x applied to y, the single argument partial function. So by the Smn theorem, I won't write but by the Smn theorem, the correct written grammar is in the LaTeX notes. There is a computable total function. There's a computable, I won't write total here, I'll just give it a total arrow so we know it's total. So such that for all x and y, so the Smn theorem will give us that, will give us this partial function in y. So s of x gives us the partial function that maps x, that maps the argument y to this partial function on the pair x, y. So in other words, phi of s of x applied to y is going to be cleanly equal to, because everything's partial, this. So phi f of phi of x sub x of y. So because S is a total computable function, it itself has an index, m, say. So let m be an index for S. So in other words, i.e., that is phi sub m equals S. So then if we feed m is in as an input to as x, as the value x here, so if we rewrite this with x is m, then s, the computable function s, that's phi of m. So phi sub phi of m, and we're instantiating with x is m, applied to y. So this partial function in y is phi of f of phi sub m of m applied to y. So we see that phi sub m of m is the number we want. So if we define n to be phi sub m of m, we have that phi sub n of y for all y is cleanly equal to phi of f of n of y. So indeed, phi n, the partial function phi sub n, is the same partial function as the partial function phi sub f of n. There's one thing I didn't explain. Why is phi sub m of m actually defined? Could potentially be a partial application here, but it's not, because phi sub m is the function s, and s was a total function. A computer, I even said total, I didn't write it, I just wrote it into the arrow here, but s is a total function. So this is, let's just put under, this is equal to s of m, so it's defined. So n is equal to s of m, so it's defined. Okay, so we found the n such that phi of n is such that the n indexed partial recursive function is the same as the fn indexed partial recursive function. So I should say that's a lot of symbol pushing. You can see it works in the symbols. Maybe you would want to double check it for yourselves. Just double check that all the results are being applied correctly. They are. Where is it coming from? Well, to talk you through where it's coming from would really take more time than we have. There's a reference in the notes to discussion in Cutland's textbook, which does this quite well. So you can look in Cutland's textbook, which is part of the literature for the course. You can find more details about Cutland's textbook on the course webpage. So you can look at that discussion here. I just want to say one other thing for the few of you in the class. For the rest of you, never mind, you can, doesn't matter if you don't follow what I'm about to say. This is just a reference for those who are able to follow it. For those of you who know some lambda calculus, there is something a bit lambda calculus-like happening here. The idea is that one can view this function here, taking an x and mapping it to phi sub x of x as a little bit like lambda. I mean, this is part of what's going on in this function as kind of lambda x, applying the function, applying x as a function to itself as an argument. So this is a bit like lambda x applied to x. And actually, because we've put an f around it, it's like lambda x f applied to, all in brackets, x applied to x. And for those of you who've looked at some lambda calculus, which I know at least a couple of you have, that is half the definition of the fixed point combinator. And essentially what's going on in the rest of the argument is like the other. I mean, basically, this is mimicking the lambda calculus definition of a fixed point combinator. We don't quite have the lambda calculus here, but we have a sufficient amount of it that the lambda calculus definition of the fixed point combinator works, and the kind of fixed point that it gives us in this situation is a number n such that the index is not actually a fixed point, but when we apply f to it, we get an index for the same partial recursive function. So it's related to the fixed point combinator in the lambda calculus. That's as much as I'm going to say about that. Well, one more thing, one can make this correspondence precise because both the fixed point combinator in the lambda calculus and this argument are both amount to a general argument about fixed points existing in something called partial combinatory algebras. But this is all much more abstract and much more advanced than this course, so I just want to leave it at that, making those links. Okay, for everybody else, and at the moment for myself, well, let's just take this as a syntactically correct proof of a rather mysterious looking theorem. And I want to end this part with an application of the theorem. As I've said, some simpler applications are going to be in the exercise class. I want to give you a more interesting application, but it's still rather short. The main application is going to be the proof of Myhill's theorem. But the first application I want to give, quite a short little application, is to give a natural example of an immune set. So we had this notion of an immune set last week. That's an infinite set that has, for which an infinite set that has no infinite computably enumerable subsets. And we had a rather tricky example of an immune set last week. Maybe that was also due to Myhill, I don't quite remember. But here's a very straightforward, well, a very natural definition of a set that turns out to be immune. So the set of minimal indices, or minimum is a better word, minimum indices. So this is a rather natural set. Well, let's call it M because it's the set of minimum indices. This is the set of all natural numbers for which it holds that E is the smallest index for the partial computable function phi sub E. So every partial computable function has actually infinitely many indices, but one can prove that. M is the set of those numbers that are the smallest indices for each partial recursive function. So for every partial recursive function, we include one number E in the set M, namely the smallest index for that function. And this is another way of defining it. And the proposition states that this set of minimum indices is immune. That is, it's an infinite set that has no infinite computably enumerable subsets. So it's a rather natural definition of a set, much more natural than the immune set we saw last week. And we're going to prove that this is immune. And the proof is rather short, and pleasingly short. So we need to show that M is an infinite set and it has no infinite computably enumerable subsets. So why is M an infinite set? Well, we know there are infinitely many different computable partial functions. For example, for every natural number n, the constant function that maps every number to n is a computable total function, and they're all different and there are infinitely many of them. So M is infinite because it contains one number for every computable partial function. And there are and there are infinitely many computable partial functions. So let's just say M is infinite because there are infinitely many computable partial functions. So the more interesting part is going to be to show that it has no infinite computably enumerable subsets. So to do that, let's suppose for contradiction, so I like to use this symbol for contradiction, that A is an infinitely computable subset of M. So is an infinite CE computably enumerable set. So by a result in, so by lecture 8, in lecture 8, we saw that every infinite computably enumerable set has an infinite computable subset. So there is some infinite computable, not just CE, but a computable, an actual decidable set. Computable, so okay, so every infinite computably enumerable set has an infinite computable subset. We know that from lecture 8. So if we have an infinite, if M has an infinite computably enumerable subset, then there's a further subset of that that's still infinite but computable. And also by lecture 8, the computable sets are exactly the images or ranges of total increasing functions, computable functions. So this is still lecture 8, and B is the range of G for some increasing, we characterize the infinite computable sets as the ranges or images of increasing computable total functions. So since G is increasing, we have that G of X is greater than or equal to X for every number X. That holds for all strictly increasing functions. Increasing means strictly increasing. Every successive number, so G of 0 is strictly less than G of 1, is strictly less than G of 2, is strictly less of G of 3, and so on. So as G is increasing, G of X is is less than or equal to X. So if we consider G of X plus 1, that's strictly greater than X. So if we consider the function f of X, if we define the function f of X to be G of X plus 1, whoops, that's supposed to be X plus 1. This is a computable function. So it is a total computable function satisfying that f of X is strictly greater than X, because it's f of X is G of X plus 1, which is greater than or equal to X plus 1. So that's strictly greater than X for all X. So now we're going to apply the recursion theorem to F. So by the recursion theorem, there exists an n, a natural number n, such that the partial computable function indexed by n is the same as the partial computable function indexed by f of n, and by definition of f, that's the same as the partial computable function. So f of n is the same by definition of f as is the same as gn plus 1. So that's the partial computable function indexed by g of n plus 1. So since g of n plus 1 is greater than n, well, if f of n, which is great, anyway, point is g of n plus 1 is greater than n, it holds that n is a smaller index for phi of n than g of n plus 1. So g of n plus 1, I don't need to even put that equals fn there. Since g of f, so g of n plus 1 is greater than n, we have that clearly n, they are both, g of n plus 1 and n are both indexes for the same partial computable function, but clearly n is a smaller index. But this contradicts that g of n plus 1 belongs to m, because m was, the point of g was that m, because clearly g of n plus 1 belongs to B, because B is the image of G, and that was a subset of A, and that was a subset of M. So by this, G of n plus 1 belongs to M, but the only numbers, sorry, this is n plus 1, but the only numbers allowed to belong to M are those numbers that are the smallest indexes for the partial recursive functions they index. And we've seen that gn plus 1 is not the smallest index for the partial recursive function it indexes. So that's a contradiction, and that proves that the proposition is true. So indeed, this is an immune set. So that's an application, a slightly involved, but not too terribly involved application of the recursion theorem. Okay, that's a good stopping point. I make it 3:57. I think we anyway deserve a full 15 minutes break, plus let's take things to the hour. So let's start again at 16:15. So let me pause the recording. Okay, so in the last part, we are going to now apply the recursion theorem to finish the proof of Myhill's theorem. So rounding off the lecture, only the bad news is, if it is bad news, I don't know, it's the bad news is that the version of the recursion theorem we have so far is not quite good enough. So this is the basic version. We need to have the full version of the recursion theorem. This is not that hard to motivate now that, given that we've already got the basic version. So suppose we've got a two-argument function, computable function. I won't bother to write that, but suppose we've got a two-argument total function. Then by the recursion theorem, for every, if we fix one argument, so for every z in the natural numbers, well, we can apply the recursion theorem to the function well, let me write it actually a little bit differently. For every z, sorry, my tablet is going, the response to my tablet is being very slow at the moment. But for every z, we can apply the recursion theorem to the function x maps onto f x z. So the point is, for z, we fix that argument and we consider the function f in the other argument to obtain a number n sub z given by the recursion theorem such that n sub z index is the same function as this function applied to f to n sub z. So this is simply applying the recursion theorem as stated above. Well, let's put it the same way around with the f on the left, just as stated literally above. So the function indexed by f of nz of z, this function applied to z, sorry, to n sub z, is the same as phi of n sub z. And the full version of the recursion theorem says we can compute nz from z. The full recursion theorem says we can compute n sub z from z. So let's state it here. Clean is recursion theorem. So I'm just going to write slowly so I can write a bit more neatly than, I think it's better to be neat. So the full version is for any total computable two-argument function now. So now, rather than there exists a number that is a fixed point for the function in the sense that it's a fixed point with respect to which partial computable functions are indexed, we now say, rather than being a number, there exists a total computable function that finds such fixed points. So for any total computable, there exists a total computable, and I'm going to call this function n. It's a bit of a, normally we use n for numbers, but in this case it's the function that given a z finds n sub z, so I'm going to call it n, such that for all z, for all natural numbers z, phi of f of n of z and z is phi of n of z. So in other words, applying n to z indeed gives us this kind of fixed point in terms of which partial computable functions are indexed for this total computable function. So it's simply a version of it's basically very similar to the original version. It just says we can compute the number n in another parameter z. So we should say that this proof is proof of the basic version. So what about proving the full version? So for your interest, the full version is proved in the LaTeX lecture notes. Whoops, I want to rub that off. I want to turn that into a full stop. So this full proof is not examinable. But if you're interested in it, it's basically the same proof as before, but with the parameter z put in the relevant places. But the statement of the full theorem is examinable. That is, there might be questions that ask you to apply the full theorem. The statement is examinable. Okay, and now we're going to apply the full version as stated to prove Myhill's theorem, and that's the last thing we need to do, and then that's the end of the course. Okay, so to complete the proof of Myhill's theorem, we need to establish so Myhill's theorem said that the M-complete sets, that's the computably enumerable sets that are as difficult as possible according to the total reducibility relation, are exactly the creative sets. We've already shown that every M-complete set is creative, so we just need to prove the converse. So we want to prove the proposition every creative set is M-complete. And then we are done. Okay, so let's suppose that B is a creative set. We need to prove that it's M complete. That means that it is computably enumerable and every other computably enumerable set reduces to it. Well, a creative set by definition is a computably enumerable set whose complement is productive. So if B is a creative set, then it is immediate that it is computably enumerable. It's part of the definition. Then B is in particular computably enumerable. So it remains to show that any other computably enumerable set reduces to B. So suppose A is a computably enumerable set. Is any computably enumerable? Yeah, let's write any just to be clear. Is any computably enumerable set? We must show that A reduces to B. So we need to define a total computable function that will turn membership of A. We'll be able to test membership in A by applying that function and applying membership in B. Okay. Now this computable function we're going to apply is a little bit going to come. How we get it requires a little bit of work, and it's again one of these arguments. It's not totally clear where we're heading until we get there, but we can think of it as follows. We've got certain amounts of information and we want to make use of the information we've got. So in particular, B is a creative set. That means its complement is so it's computably enumerable and its complement is productive. So because the complement of B is productive, there's a total computable function, G, that given the index for a subset, for a computably enumerable subset of the complement of B, will produce an element of the complement of B that's not in that subset. That's the definition of productivity. So let G be such a function. And I'm going to say that such functions witness so that's a witness to the, so suppose G witnesses the productivity of the complement of B, by which I mean G is a function that given an index E for a computably enumerable subset of the complement of B will give us that an element G of E such that G of E is a member of the complement of B that is outside that the given computably enumerable subset. So given this total computable function G, we're going to use it to define a partial computable function in 3 arguments. So the fact we use 3 arguments is a little bit of an indication that there's something non-trivial going on in the argument, in the proof. So we're going to define a partial computable function. Let me make it clear that that's a 3 in 3 arguments. And this is, so the 3 arguments, let's call them X, Y, and Z. And it's cleanly equal because it's partial. And we're actually going to make this function almost never defined. When it is defined, it's going to return the number Z. It's only going to return the number Z if, in the case that Z is G of X, and y belongs to the computably enumerable set A. And otherwise, it's going to be undefined. So this is computable because given an x, y, and z, we first check to see if y belongs to A. That's a semi-decidable property because A is computably enumerable. So we perform the algorithm to see if y belongs to A. Maybe it goes into a loop, in which case that's no problem, because if y doesn't belong to A, then the result of f is undefined. So going into a loop is fine. If y does belong to A, because A is semi-decidable, eventually we get the information, yes, y belongs to A. We then say, okay, great. Let's look at g of x. G is a total function because the computable function that associated with productivity is always total. So g is a total function. So we compute g of x and we just check to see if that's equal to z. So notice for any fixed x and y, there is at most one value z on which fxy of z is defined. If y doesn't belong to A, and if, well, in fact, if y belongs to A, then there is exactly one value z for which fxy z is defined, that is g of x. And if y doesn't belong to A, then for the fixed x and y, then the resulting function in z is not defined on any values of z. So this is a partial computable function. So as usual, we're going to apply the Smn theorem and to reduce it to a single argument function. So here we're going to take the arguments x and y as a package. And so we've taken those as given. And from that, we're going to use the Smn theorem to give us an index s of x of y. So the Smn theorem will give us a total computable function s, which will give us an index s of x of y for the resulting function in z. So by the Smn theorem, there's a binary computable. A binary just means two arguments. Well, let's write the two arguments in here as well. So such that, so it's taking two natural numbers as arguments, so that given x and y, s applied to x and y will give us an index for the function in z that computes f of x, y, and z. So in particular, if we look at the domain of this function, I've already talked about the domain of the function. If we fix values of x and y, so the domain of the function phi of s of xy, so remember w of the index e is our notation for the domain of phi of e. So the domain of this is, well, I've already talked you through this. In the case that y belongs to A, is just a single, this was defined only on one value z, and that value is g of x. G is a total function, so g of x is always defined. So this is if y belongs to A. And in the case that y does not belong to A, then f of x of y of z is defined on no values of z. So in that case, phi of s of x is defined on no values of z. So the domain of phi of s of x, that's phi of s of x of y. The domain of that, that's w of s of x of y, is the empty set. So if y does not belong to A. So now we're going to use the recursion theorem, the full recursion theorem on the function s of x of y. So by the full recursion theorem, applied to the function s of x of y, there is a computable total function, which I'll again call n, satisfying that when we apply s to n of, I'll use y instead of the z in order to be compatible with what I've got here, in the z in the recursion theorem. But the point is, n of y, n is finding in the argument y this fixed point that's giving us, when we apply the s function to it, and that's the same, defines the same, gives an index for the same partial function as that given by n of y. So this holds for all natural numbers y. So these are the same partial functions. So in particular, they have the same domains. So in particular, the domain of s of n of y is the same as the domain of the function indexed by n of y, because they're the same function, the same partial function. So let's call this A, and let's call this B. And combining these two, we have that, well, the W of the domain of the function indexed by S of x of y for any x and y. So if we instantiate that with n of y and y, so that's the same as the domain of n of y. So the W, so combining A and B, the domain of the function indexed by n of y is the domain of the function indexed by S of n of y, y, which is which is this, but with n of y instead of x. So this is equal to g of n of y if y belongs to A and the empty set otherwise. Okay, so you may wonder where on earth we're heading, but we're now in a position to complete the proof, because we can now give the function that reduces A to B. So we shall show that the function g composed with n reduces A to B. So we need to show that for any y belongs to A if and only if g of n of y belongs to B. So we're going to prove firstly that y belongs to A implies g of n of y belongs to B. Let's prove that. So suppose y belongs to A, and And suppose, for contradiction, that G of n of y does not belong to B. So let's call this C here. So by C, the domain of n of y is the singleton set consisting of G of n of y. So because G of n of y does not belong to B, that's saying this singleton set, well, this element belongs to the complement of B, so this singleton set is a subset of the complement of B. So W of n of y is a subset of the complement of B. But the complement of B was productive, so for any index of a subset of the complement of B, G applied to that index will give us an element of the complement of B that's not contained in this set. So by the product, since G is a witness to productivity, of the complement of B, G of n of y, so applied to this index is a subset of the complement of B, so G of n of y belongs to the complement of B, but is outside that subset. But this contradicts that G of n of y actually does belong to the subset n of y. The sum does belong to the set W n of y, which we've got here. So this contradicts that W of n of y is G of n of y. So that finishes that particular implication. So we just need to show the other implication that if G of n of y belongs to B, then y belongs to A. And we'll prove that in the contrapositive. So we'll show that if y does not belong to A, then G of n of y does not belong to B. So this is a little bit easier than the previous argument. So suppose y does not belong to A. So by property C, the domain of the partial recursive function indexed by n of y is empty. So by C, the domain of partial recursive function indexed by n of y is the empty set. And of course, the empty set is always a complement of, the empty set's a subset of anything. So it's certainly a subset of the complement of B. So again, since G is a witness to the productivity of the complement of B, so now G of n of y let's even say, since G witnesses productivity, G of n of y, again, belongs to the complement of B and is outside this subset, but this subset was the empty set, so it's trivially outside that subset. But that's what we wanted to show, that G of n of y does not belong to B. So that as required. And we're done. That's it. We have shown by these two implications that we've shown that y belongs to A by these two implications if and only if G of n of y belongs to B. In other words, the composite function G composed with n is a reduction from A to B, and that shows that all we assumed for A was that it was a computably enumerable set. All we assumed, we started off with B being a creative set, and we used that to show that any computably enumerable set reduces to B. So B is indeed M complete. And that completes the proof. And that basically completes the lecture. And that then even more substantially completes the course. So rather a technical end to the course. If we had another lecture, I would probably give a less technical finish to the course, but I did want to include this material because the recursion theorem in particular. So as I say, the Myhill's theorem is a theorem that one can motivate in sort of general terms, because the concept of classifying how complicated sets are computationally, that makes sense. And this is one way of doing that. And it's interesting to see that there are sets that have the most complicated classification among the computably enumerable sets. And it's nice to have this explicit characterization of them given by Myhill's theorem. So it's a result that almost speaks for itself in some respects. But actually the recursion theorem is the thing I most wanted to do in the lecture, because it is a very curious theorem. It's the kind of theorem, if you get into the material, to try to think about what it means. We've had two applications of it in this lecture. There'll be some easier applications in the exercise class. And for those of you who know something about lambda calculus, there are the connections with the fixed point theorems of lambda calculus. Anyway, it's a curious theorem, and I refer you with a recommendation to the Cutland textbook, which is the main textbook for this course, if you're interested in reading more about it. Anyway, it's 10 minutes before the official end of the lecture, but I think that is plenty of material for today, especially as it was quite technical. So I'm going to say goodbye on the recording now and end the recording.